Hello everyone, welcome to the fifth lecture of this module 2 on microsensors and nanosensors. We were discussing the characteristic of sensors. In this, we discussed limiting errors in the previous class. Let us see what are the different sources of errors. We have seen different sources of noise in previous class. Okay, let us see different sources of errors. So, error arises from different sources in sensors and they are classified as gross errors, systematic errors and random errors. Systematic errors can be of three types: instrumental errors, environmental errors and observational errors. We will see them in little detail so that we have full command on errors, and when we start discussing about different sensors from module 3, we will be able to utilize all of this. Okay. So, let us see what is gross errors and can we minimize it or not. Okay. So, gross errors mainly include human mistakes in reading the sensor's output, recording it and calculating the sensing data. When I say calculating the sensing data, I also mean interpreting the sensing data. Okay. Say for example, since we are discussing mostly electrical sensors where the output is in the electrical form, you already know this because we have discussed this in module 1. The electrical output is in the form of current, voltage or in the form of charge. So, but we have to interpret from that current or voltage to some physical parameter. Say for example, consider a case of a temperature sensor. The output is in the form of some microvolt or something, right? Now, I have to interpret this microvolt for certain temperature. Okay. So, it also include that kind of error, interpreting error. Okay. The experimenter may grossly misread the scale of the sensing device. Okay. So, if it is an analog sensor, okay, and if the output is say 12.01 milliamp, okay, the experimenter may totally say misread the data that it is showing. Okay. Say let us consider one example of a temperature sensor. Okay. So, due to oversight, an experimenter may read temperature from a temperature sensor as say 34.5 degrees Celsius, while the actual reading can be say 24.5. Okay. So, he misread these three as 2. Okay. So, gross errors, you cannot say that what amount it will be, it can be of any quantity. Okay, because you never know that the person is reading this 3 as 8 or as 2. Okay. So, it is really impossible to actually find out that what value he is going to. Okay. So, their mathematical analysis is actually impossible because it is totally a random event. Okay. Gross error can be avoided by adopting two ways. One is great care should be taken in reading and recording the data from the sensor. Okay. And more than one reading should be taken for the quantity which is under measurement. Okay. So, if this person has recorded this 34.5 degrees Celsius multiple times, okay, so this is just one data that he has taken as 24.5, but if he has taken multiple data like say 3 or 4 events, this error can be minimized, okay, or even sometime can be avoided. Okay. Now, let us see systematic errors, which is very important in the microsensors and nanosensors domain. Okay. As I have already mentioned that these can be divided into 3 different categories. One is instrumental errors, then environmental errors and observational errors. Let us see them one by one. Okay. What are instrumental errors? These errors arise due to 3 different reasons. The first reason is inherent shortcoming in the sensing device. Second is misuse of the sensor. Okay. And third is loading effect of the sensor. So, these instrumental errors can be because of these 3 reasons. Okay. And this name arises from the fact that actually these sensors are either you are using it as an instrument or it is a part of instrument. Okay. So, let us see these causes in little bit detail. Okay. And let us understand what are these causes. First is inherent shortcoming in the sensing device itself. Okay. This may be due to construction of the sensor. its calibration or operation of the sensing device. Okay, these errors can cause the sensor to read either some very low data or it may give you some very high value. Okay, then second is misuse of the sensor. Okay, so error occurs in these measurements are due to the fault of the operator than that of the device. Okay, so basically you are misusing the sensor or the operator is misusing it. Okay, so you can understand it as a good sensor used in an unintelligent way. Of course, if you are using it in unintelligent way, it can give some erroneous result. Say a good example can be a failure to adjust the zero of the sensor or poor initial adjustment. Okay, so we can use the different static characteristics that we have seen in our module 1 and module 2 to understand this misuse of the sensor. Okay, and since we are taking an example of gas sensor for understanding all of these, let us try to see how it can be misused. Okay, say I have a two terminal sensor, say a chemiresistive device, which dynamic range has been prescribed by the say manufacturer as say 4 to 40 ppm of some certain gas, say H2S or say ammonia. Okay, now what I have to do is I have to make use of this sensor in the region where I expect the ammonia concentration in the range of 4 to 40 ppm. Say if I expect that okay the concentration is going to be say 4000 ppm of ammonia, okay, I should deploy other sensor, not this sensor. If I am using this sensor of this particular dynamic range in this area, I can say that it is basically a misuse of the sensor. Now, even in the condition of this misuse, if you are using it, okay, so the idea was to use it in between 4 to 40 ppm, right? Now, the concentration is say 4000 ppm. What will happen to the sensor? We have discussed that it is not going to fail. Okay, what it is going to do is it is going to saturate. Okay, now say I have a very good, very precise sensor film, okay, on which I have exposed 4000 ppm of ammonia gas, okay, and in place of and this 4000 has come in place of 40 ppm, okay, the sensor or the receptor film was made to be exposed not beyond 40 ppm. Now this person is misusing and exposing it to 4000 ppm of ammonia, right? What will happen? This, if you see the fictitious say transfer function or a dynamic plot, okay, ideally in case of 40 ppm, I was expecting something like this, okay, say this is current versus time, okay, for 40 ppm, okay, and at this point I have exposed it, okay, and at this point I have switched off ammonia, okay. So this is a switch off condition. All right. Now the same, let's see how typically it will look for 4000 ppm of gases. Okay. So when you expose it to 4000 ppm of ammonia, the maximum will not be achieved immediately, right? Apart from this physioabsorption or some say weak chemiabsorption, there will be some strong chemiabsorption because of the presence of very high concentration of this analyte, okay. In this case we are considering ammonia, right? So it is going to saturate at some very high time at say t is approaching to infinite or so, okay. Now say it has not reached to some saturation, okay, but it is keep on saturating, okay, it doesn't saturate, okay. Now when you switch it off, okay, again this is not going to come at its baseline, okay, it will be say somewhere here or somewhere here, it is not going to reach this point. Means that there are certain ammonia gas which is already adsorbed on the surface. Now for the next cycle, if you are going to use it for say 40 ppm, okay, for this case it will be repeated, Okay. For this case, it will be repeated like this, but here the baseline will start from somewhere here, right? Somewhere from here, right? Of course, the second time the baseline will reach somewhere here, okay, right? So what I missed the zero setting of the sensor, okay. Now how to set it to zero, okay? I can use several techniques like heating this surface to certain temperature to get rid of this ammonia molecule which is adsorbed on the surface, okay, or I can use some pulse or some laser kind of thing to get rid of or I will provide some external heat, okay, or external light to remove this ammonia molecule from the surface adsorption behavior, all right. So if I did not do the zero adjustment to the sensor, okay, my first reading is wrong, my second reading is also going to be wrong, okay. So two conditions we have seen. One is misuse of the sensor, means I am using it beyond the dynamic range, okay, and second misuse that I have done is I have not done zero setting over here, okay. I hope that this is clear to you. Then third is loading effect of the sensor, okay. Say when the sensor is attached to a circuit, okay, this should not load the circuit. Loading means there should not be very high voltage drop across the sensor, or the sensor should not draw more amount of current, okay, as you know, we already have decided that, okay, the sensor should take this much amount of current, but if it is taking more than that or much higher than that, okay, this condition is loading effect, and in that condition we will see some error, okay, and that is a part of this instrumental error, okay. So I hope that instrumental error is clear to you. Then let's understand the environmental errors, okay. These errors are due to conditions external to the measuring device. This includes condition in the area surrounding the sensing device, okay. These may be effect of temperature, pressure, humidity, dust, vibration, or some external magnetic or electrostatic fields, okay. Environmental errors can be reduced by following corrective measures, okay. Arrangement should be made to keep the condition as nearly as constant for these sensors, okay. For example, if I am developing some sensor in a clean room in IIT Guwahati, okay, and I have tested all these conditions at say 50% RH at 25 degrees Celsius, okay, and I have not checked it at 75% RH or say 90% RH, okay, or at different temperature, and I do not take care of these things, okay, and if I will try to deploy this sensor in a very humid condition, okay, at some place, okay, which is near to seaside, okay, my readings will be totally erroneous in nature, right. So arrangement should be made to keep the condition as nearly as constant, okay. We can do some local ambient conditioning, nowadays people are using that, okay. Then we should also use sensors which are immune to these effects, okay. Usually it's very difficult to make the sensor which is immune to ambient conditions, okay. Then if it is suspected that external magnetic or electrostatic fields can affect the reading of the sensor, magnetic or electrostatic shielding can be provided, okay. So if I know that the operating condition of my sensor is such that there is some external device there which can produce a magnetic field, and my sensor is susceptible to, you know, change its values or change its output in presence of these factors, we can provide some external shielding, okay. Then people try to correct this data or take care of the environment conditions by some computational techniques, okay. There are various compensation circuits through which also you can minimize the effect of this baseline drift or change in the sensor's property, the output properties in different temperature and different pressure conditions as well as different humidity conditions. Okay. Next is observational errors. Okay. There can be many sources of these errors. Okay. One of the typically given example is shown over here. Okay. Pointer of an analog sensing device rests slightly above the surface of the scale. Okay. An error on account of parallax will be incurred unless the line of vision of the observer is exactly above the pointer. Okay. Now, say if someone want to read this device, okay, this scale is slightly, it can be seen little towards little right when you are seeing from this direction. Okay. Now, if you are seeing from this direction, it will look like it is little bit, to the left side of this 150 scale. However, when there is no reflection, it will look like it is exactly on 150, and this is known as parallax. Okay. And again, you should observe it correctly. Okay. And this is coming due to observation. These are categorized under observational errors. Okay. So with this, we have understanding of different errors as well as different sources of errors. Okay. So with this, we have finished the static characteristic of sensor. Okay. Now let us see some dynamic characteristics of the sensors also. Okay. So the sensors are subjected to different input stimuli, okay, which are actually not static but are dynamic in nature. Okay. Say for example, if you are trying to measure temperature is always changing. Okay. It's not constant in nature, particularly when some sensor is deployed. Okay. So sensors are deployed only there where there is a chance that there is variation in the temperature. Okay. Then the input varies or the stimuli varies from instant to instant, and therefore output also changes. Okay. The behavior of the sensor under such condition is described as dynamic response. Okay. So dynamic response can be understood with something which is varying always with time. Okay. So dynamic inputs are of two types, and so our dynamic systems are transient and steady state. Okay. The response of a sensor subjected to a time varying stimuli like a sudden change in temperature can be divided into two parts, very similar to what you have seen: a transient response and steady state response. Okay. So if CT say is the total time response of a sensor or a sensor system, okay, CT can be written as like this: C subscript T plus CSST, where CT and CSS denotes the transient and steady state response of the total response. Okay. So the total response has two parts now. One is transient response and another is steady state response. Let us try to understand what I mean by transient response and what I mean by steady state response. Okay. For sensor, the steady state response is simply the response when time reaches infinity. Okay. So transient response is defined as the part of the response which goes to zero at at time equal to infinity, or when time becomes very large. Okay. So therefore the component CT has the property of this. So when t tends to infinity, CT, which is a time varying function, okay, becomes 0. Okay. So as I have already seen that the CT is divided into two response, CT plus CSS. Okay. Of course both are a function of time. Okay. So therefore after this time, when this t is very large or when it is reaching infinity, the sensor response is CT is equal to CSS only, because the CT portion has become 0. Okay. And this CT equal to CSS is known as the steady state response of the device. Okay. So this is all about the dynamic characteristic of the sensor. Okay. Now dynamic behavior of the sensor. Now let us understand the dynamic characteristic of the devices. Okay. We have seen different static characteristic of sensors, which include the linearity, then repeatability, reproducibility, span, transfer function, etc. Okay. However, all the dynamic characteristics of the sensor can be divided into 4 different types. First is the speed of response, at which speed these sensors are responding. Okay. Second is the measuring lag. Third is fidelity, and fourth is the dynamic error. Okay. let us understand all of these three one by one. Okay. First is speed of response. Okay. This speed of response is defined as the rapidity with which a sensor responds to changes in the measured quantity. Okay. And this is denoted, or this speed of response take care response time and recovery time. So if the response is fast and recovery is fast, I can say that the speed of response is fast. However, if any of this is slow, okay, let's plot two characteristic or even three characteristic and try to understand that which is fast and which is slow. Okay, and of course this is coming from dynamic plot. Okay, we have discussed dynamic plot a bit when we were discussing the static characteristic also. Okay, so again this is current and this is time. Okay, all right. The sensors, let's consider three different conditions. These are three different conditions. If you see condition 1, okay, the analyte is subjected over here, okay, and it reaches to this value where the analyte has been removed in all the cases. Okay, here the analyte has been introduced and at this point it has been removed. Okay, so this double arrow suggests that it has been removed and the single arrow suggests that it has been introduced. Okay, now if you see, say this is T1, this is T2 for all the cases. T1 is the time at which it has reached to maximum. We will define response time and recovery time later, but let's understand this curve first. Okay, so T1 is the time at which it has reached to saturation and the analyte has been switched off. Okay, for all the conditions. It is coming to some other point. Okay, I cannot show it on this screen, so it is at some very large time. Okay, now the speed of response is governed by T1 plus T2, right? So in this case, T1 and T2 are in moderate quantity. Neither T1 nor T2 is a very high quantity. Okay, so I can say that the speed of response of the sensor is decent. Okay, however, in this condition, T1 is very large, although T2 is very low, but T1 is very large as compared to T2. So overall behavior is governed by T1. But since T1 is itself is very large, even T2 is very small, I can say that the sensor is slow. Okay. Similarly, for condition 3, although T1 is not very high, but recovery is very poor. Okay. So it is recovering at very high, at T equal to infinity. Okay. So I have a condition where T1 and T2 is nearly equal to T2, where T2 is very high. Okay. Then also I can say that the speed of response is very low. Okay. However, in these two conditions, if you see, either this response is saturating at very high time, or recovery is coming at T equal to infinity or some point. Okay. Then comparing this condition 1, 2 and 3 is kind of injustice. Okay. So although this saturation is not coming, but from this point somewhere, or if you have switched it off at somewhere here, okay, we understood that okay, it's not going to increase beyond this. Okay, and although it started decreasing, the current started decreasing at some other time. Okay, now when it is very difficult to compare all these three conditions, okay, and therefore the response time and recovery time has defined by some other definition. Okay, let's define it properly. Okay, now consider this case where recovery is going to happen at T equal to infinity or so. Okay, baseline is not recovering. Okay, so the response time is defined as the time to reach 10% of the baseline to 90% of the saturation value. Similarly, recovery time is defined to reach from 90% of this to 10% of the saturation line or the saturation of this baseline. When I am talking about saturation, I am talking about this value. Okay. So this is baseline. So 90% of the saturation value to the 10% of the exact baseline. Alright. So if you define like this, then comparing that three conditions is not that difficult. Okay. 90% of saturation you can achieve. Okay. Of course, then also in condition 2, T1 will be very high. Okay. Similarly, T2 will be very high in condition 3, but then also I am able to quantify the time. Alright. So this is speed of response. Second is the measuring lag. Okay. The second dynamic characteristic is the measuring lag. Okay. So it is the retardation or delay in the response of a sensor to changes in the measured quantity. Okay. The measuring lag are of two types. One is retardation type and another is time delay lag. Okay. Let's understand the retardation type and the time delay lag. Okay. In the retardation type, the response of the sensor begins immediately after a change in the measured quantity that has already occurred. Okay. However, in the time delay lag, the response of the sensor begins after a dead time, after the application of the input. Okay. So dead time simply shifts the response of the system along the time scale. Okay. Dead time, I don't have to define it once again, but dead time we have discussed in the module where we have discussed the steady state response. Okay. So dead time is the time in which even you are changing the input, output is not changing, right? Then third is the fidelity. Okay. So it is defined as the degree of closeness to which a sensor indicates changes in the measured quantity without any dynamic error. Okay, we will define the dynamic error in the subsequent slides. Okay, suppose if a linear varying stimuli is applied to a sensor, okay, and if the output is also a linearly varying quantity, I can say that the sensor is having 100% fidelity. Okay, so ideally a sensor should have actually 100% fidelity and the output should appear in the same form as that of input and there is no distortion produced in the signal by the system. Okay, please note that fidelity is not only defined for linear sensors, but it can also be defined for non-linear sensors. Okay, when I say linear sensor and non-linear sensor, I am indicating its transfer function. Okay. So in the definition of fidelity, any time lag or phase difference between output and input is actually not included. Okay. So you have to take care of these two, time lag and phase difference separately. Okay. Then the final dynamic characteristic of a sensor is the dynamic error of the sensor itself. Okay. So we have already seen different static errors. Okay, but we have not seen dynamic error till now. Okay, so dynamic error is the difference between the true value of the quantity which is under measurement changing with the time and the value indicated by the measurement system if there is no static error assumed. Okay, in that condition the difference gives you the dynamic error. Okay, this dynamic error is also known as measurement error. Okay, the total dynamic error of the sensor is the combination of its fidelity and the time lag or phase difference between the input and output of the sensor. So dynamic error actually take care both fidelity and the time lag or any phase difference between output and the input. Okay, so with this we also understood different dynamic characteristic of a sensor. Okay. So with this we are actually also completing our module 2. Okay, we will meet in module 3 with the discussion on some chemical and humidity sensor. We are taking example of gas sensor continuously, but we have actually not described gas sensor in detail. So in this module 3 we will also define that. Thank you.